Good morning, everyone. Welcome. My name is Dan Quigley with DSI. Thank you for joining us for the Gleeble webinar series. This is our 45th webinar, and I hope you've all had a chance to view all of our previous webinars. If you did miss one, they are all available online, so please feel free to binge watch them all. I'm sure you can learn a lot more from our webinars than from binge watching some silly Netflix series, but that choice is up to you. We have about 100 people registered to attend today, and looking through the attendee list, we have some of really the best research institutions and manufacturers in the world represented here today. So we are all in good company, but as always, we are grateful for your time. It's our honor to help you in the important work that you are doing, and we will endeavor to make sure that this time is valuable for you. The title of today's webinar is Investigation of Manufacturing Processes for Automotive and Biomedical Applications using Gleeble Systems and Physical Simulation. The session will include two presentations from the great research teams at Politecnico de Bari in Italy. The first presentation addresses investigations about the solid-state foaming of a titanium alloy produced by hot isostatic pressing. It will be presented by Antonio Piccinini and Pasquale Guglielme. This is a unique presentation in the Gleeble webinar series as it explores biomedical applications, which isn't something we see a lot of, but it is obviously very important, and it's really cool to see how the Gleeble can support that work. The second presentation will be led by Manuela Palmieri. She will share how she combined finite element analysis with physical simulation for an efficient design of thermomechanical press-hardening processes. I've been able to see this presentation already, and it does a great job of illustrating the relationship and codependence of FEA and physical simulation. As always, our goal will be to keep this webinar to 1 hour or less. We should have a few minutes at the end of the presentation for some live Q&A. If you have questions, please submit them using the chat feature here in the webinar. We usually only have time for a few questions, so if needed, we can connect you with the presenters or our team for an offline discussion. Video of this presentation will be available online soon. You'll be able to find a link to this video as well as videos of past webinars by going to our website at gleeble.com and clicking on the resources link in the top navigation bar. Then click on webinars where you can view past webinars and sign up for future webinars. I'm excited about our next session on October 21st, which will be presented by Dr. Richard Baumer from Latorno University in Texas. He'll be sharing some of his team's work, and as many of you know, Latorno has a long history of really impressive welding research, so we're looking forward to learning about the work that Dr. Baumer and his team are doing down there in Texas. But without further ado, it's my pleasure to hand this over to the team at Politecnico de Bari.
Good morning to everyone. My name is Antonio Piccinini. I'm a research associate from Politecnico di Bari at the Department of Mechanics, Mathematics and Management. I would like to thank the DSI for giving us the chance to present some results from our latest research project. In particular, today I'm going to talk about the investigation about the solid-state foaming of the titanium 6 aluminum 4 vanadium extra low interstitial produced by hot isostatic pressing. I'm sharing this presentation with my colleague. I will start and then I will pass the stage to my colleague who will illustrate more technical data and more results from the activities I'm starting to present. So let's start the topic with the current state and the new perspective of bioimplants, in particular, how the prosthetic market is expected to grow in the next period from 2021 to 2028. The key aspect is that designing a processes must follow different criteria so that the bioimplants should be able to respond to some functional requirements, for example, structural integrity, corrosion resistance, or biocompatibility. And this can be achieved by selecting a proper material. On the other hand, the implant must respond to some aesthetic requirement, so it has to be custom made, so it has to be perfectly respectful of the patient morphology, must ensure higher level of geometrical complexity, and once implanted should not cause any asymmetry in the patient morphology. And this can be achieved by properly selecting the manufacturing process. So the combination of material and manufacturing process can give us the chance to achieve a new category of prostheses of customized implants. In particular, the objective of one of our latest research projects, the research project FABRICARE, is to obtain a new typology of implants, literally a hybrid implant, a hybrid prosthesis, characterized not only by a high geometrical complexity, but also by the presence of bioactive and antibacterial surfaces. The flow of the activity is reported on the left, starting from the identification of the product requirements in terms of material, in terms of geometrical complexity, in terms of zone of the patient to be healed. Then, from these data, the process can be designed and the prosthesis can be manufactured, and after the manufacturing, outer surface can be functionalized. Then, all this data has to be uploaded in an integration platform whose main role is to reduce the distance in terms of knowledge between doctors, process engineering, and biomedical engineer, so that the final outcome is the development and the implementation of a new clinical protocol. But beside this, one of the key aspects, one of the key goals to be achieved during this project is the manufacture of a B-layered hybrid prosthesis. So a prosthesis that, first of all, has to be respectful of the bone geometry, of the patient's morphology, but has to be characterized by the presence of a double layer, and these two layers are diffusion bonded each other. The first layer is made of bulk material, so bulk titanium, and the other layer is based on a closed cell structure, so a sort of foam structure, for two main reasons. The foam structure is able to speed up the bone regrowth once the prosthesis has been implanted, and the cell structure can be loaded with some drug agents, so improve the bioactive and antibacterial capability of the prosthesis. The big problem when dealing with the titanium and the cell foam structure is that this kind of structure cannot be achieved by starting from the titanium in the liquid state, since at the higher temperature the titanium is highly reactive. So the only way is to process the titanium at the solid state according to a specific type of procedure that is called hot isostatic pressing. So the starting point was the selection of the titanium powder. We focused the attention on different powder size. My colleague will give you later on more technical details. We prepared different type of steel can, as you can see here, because each steel can was then filled with the titanium powder, and the air inside the steel can was evacuated, and after that each can was backfilled with argon gas. At the end of this step, each steel can was filled with pressurized argon inside and titanium powder. This steel can was then subjected to the real step of hot isostatic pressing, so it was basically pressed under a specific level of pressure at a certain temperature and for a specific amount of time. At the end of the hot isostatic pressing, the steel can was removed by machining, and what we obtained was this series of billets, each containing the compacted powder and some argon bubbles, so some pressurized gas inside. If we look let's say microscopically, at the structure of the billets after the hot isostatic pressing, then, as shown here, we can see an almost homogeneous structure, an almost homogeneous state with only some small porosity. And I want you to focus on the concept that each porosity contains inside pressurized argon gas. In order to obtain the formed structure, this kind of uh, um, material state has to be subjected to different type of heating test. So what we did was basically extract some specimen from the billets. Those specimens were then subjected to Gleeble heating test. We carried out two different type of tests, a cycling one and a constant temperature one. So the former was based on changing, increasing and decreasing the temperature over a specific amount of time. The latter was based on a simple heating test, holding the temperature at a constant level. And thanks to the increase of the temperature and the lowering of the yield point of the material, then the pressurized gas could act as a kind of loading force and improve and increase the porosity and then move from the initial structure to this formed structure.
Thanks, Antonio. I'm Pasquale Guglielmi, researcher at the Polytechnic University of Bari, and as anticipated by my colleague, I will briefly describe the main phases and results concerning the characterization of the foaming process using the Gleeble system. In particular, the titanium powder were screened and sieved to obtain the correct particle size ranges. And as shown in the two figures on the left, this classification process was carried out inside a glove box and in a controlled atmosphere to avoid external contamination. In the present experimental activity, the attention was focused on two different hot isostatic pressure conditions with a powder size up to 50 and 100 microns respectively. Finally, to perform experimental tests with the Gleeble system, as possible to see on the right, the dog bone sample were extracted from each billet by means of wire electrodischarge machining. As previously said, two types of foaming process were carried out using the Gleeble system. In the first case, keeping the temperature constant, and in the other case, by varying the temperature cyclically between two different values. All the heat-treated sample then were properly prepared thanks to the grinding and the polishing procedure, and subsequently evaluated by means of light microscopy and image processing. The Gleeble system present in our laboratory at the Polytechnic University of Bari was used for all experimental activity. During each test, while the center of the sample is heated, the grip are constantly cooled. By exploiting this architecture of the system and by instrumenting each sample with 4 K-type thermocouple with a step of 10 millimeters starting from the center, it was possible to acquire a parabolic temperature profile as shown in the graph on the center. For the isothermal condition, a constant temperature of 1020 Celsius degree was imposed on the thermocouple at the center. On the other hand, for the thermal cycle, the temperature range from 920 to 1020 Celsius degree with a heating rate equal to 1 Celsius degree per second. Finally, 4 different test duration were considered from 60 to 240 minutes with a step equal to 60 minutes. The temperature profile obtained for each of the two methodology are shown in the two graphs on this slide. Considering a longitudinal length of about 30 millimeter, starting from the center of the sample, it is possible to observe for both cases that the recorded temperature variation is about 85 Celsius degree. Furthermore, on the left, it is possible to observe the sample during a test in the starting condition and at the end of the test. On the right, instead, we can observe with reference to the starting sample after electrodischarge machining the effect of the foaming process in terms of sites. In fact, a marked increase in volume and in particular in the calibrated area of the sample is visible in the two cross section. At this point, let's move on the main results obtained. With reference to the isothermal condition for a maximum powder size equal to 50 micron, it is possible to observe from the graph on the left that there is a marked effect of time and temperature on the foaming behavior. The average size of the porosity, but also the percentage of the porosity, increase with the temperature and the total duration of the test. The average size of this porosity are also shown in the micrograph on the right, and the micrographs confirm what is observed in the graph. In fact, starting from the right to the left, it is possible to observe that the level of porosity increase with the temperature recorded during each test. The same consideration can also be valid in the case of a thermal cycle. In fact, an increase in terms of porosity is visible according to the duration of the process. In this case, contrary to the isothermal case, a low effect is due to the temperature gradient recorded in the longitudinal direction of the sample, as also shown by the micrographs on the right. Moving from right to left, the temperature and the porosity increase, but the porosity level for the 20 millimeter in the center of the sample can be considered almost constant. Comparing the two different methodology adopted with the same material investigated, it is clear that, in accordance with the state of the art, the adoption of a thermal cycle promote the porosity growth in the material. With reference, for example, after 4 hours, the adoption of a thermal cycle lead to double the average size of the porosity recorded in correspondence with an isothermal heat treatment from about 20 to over 40 microns. Furthermore, the effect of the different duration of the test seems to be much more evident in the case of the thermal cycle. This results is particularly evident if we look at the micrographs show on the right. An increase in porosity is visible from left to right, especially in the case of the thermal cycle, the 4 micrograph on the bottom part of the slide. Considering the same type of the heat treatment, another interesting results coming from the comparison of the two different material investigated If we observe the comparison proposed for an isothermally treatment, the two material seems to show, at last for the test up to 4 hours, a similar behavior. A slightly higher porosity was recorded in correspondence with the maximum size of the titanium powder equal to 50 micron. On the contrary, the behavior of the two materials differ drastically when we consider the comparison based on a thermal cycle. In fact, in this case, the porosity of the material with a maximum titanium powder equal to 50 micron is larger than the other one, especially for a long time, 3 and 4 hours. This is true for the percentage of porosity as shown on the left, but also for the average diameter on the right. The comparison of the micrographs obtained for the two different type of material and the two methodology adopted also confirm the results previously discussed. To better understand regarding the material with the titanium powder dimension equal to 100 micron, a non-uniformity of the porosity sites was recorded. In fact, they apparently seem to be larger than those of the other material, but the presence of very small porosity determine a reduced average value. Finally, the comparison with the existing references based on comparable starting condition and with reference to the thermal cycle condition show a greater foaming capability of the material investigated in the present work according to the different investigated condition. Furthermore, with reference to the initial diameter of the titanium powder, the foaming process seems to be emphasized by low value. To summarize, the use of the Gleeble system to study the foaming process for titanium alloy was useful for the purpose of the research project. In particular, the high precision of the imposed cycle and the presence of a thermal gradient in the sample made it possible to study the phenomenon extensively. As regard the two different conditions of the material, considering the same temperature, time, and method adopted, a smaller size of the titanium powder allowed to obtain a greater final porosity. Even the literature seems to confirm the trend experimentally recorded. Finally, the results deriving from the first part of the activity related to the FABRICARE project motivate an extended adoption of the proposed methodology to all the other available sample. I finished and I would like to thank everyone for the attention.
Great presentation. Thank you, Antonio and Pasquale. Biomedical prosthesis is such an interesting and important application, so I'm glad that we were able to feature this work in our webinar series, and thank you both for presenting. If you have any questions, please feel free to type them into the chat area. We'll hold a live Q&A until after the second presentation is complete. And with that, I am happy to introduce Manuela Palmieri, who will be presenting her work combining finite element analysis with physical simulation for an efficient design of thermomechanical press hardening processes. And I'll turn this over to her.
Good morning, everyone. I'm Palmieri Maria Manuela, and I'm a PhD student from Politecnico of Bari in Italy. My tutor is Professor Luigi Tricarico, and for my research activities, I adopted the Gleeble system to physically simulate some manufacturing process. For this webinar, I will speak about a physical simulation to investigate the press-hardening process for automotive application. Therefore, in this slide, I put images about the physical simulation of manufacturing process laboratory where the scientific coordinator is Professor Luigi Tricarico, and some images about advanced forming manufacturing laboratory where the scientific coordinator is Professor Gianfranco Palumbo. In these two laboratories, there are some equipments adopted for my research activities. In particular, on the left, you can see the Gleeble system adopted for physical simulation tests. A spot welder to weld thermocouples on a specimen to be treated with the Gleeble system. Moreover, here we see an Instron universal test machine adopted for tensile tests. And you see also a digital image correlation system adopted to assist tensile tests. On the contrary, on the right, you see a lapping machine adopted to grind and polish specimen and the cureness hardness tester adopted to carry out hardness test. As we will see during the presentation, the finite element code, in particular Autoform and Console, support these laboratory activities. During today's presentation, I will focus the attention on the support offered by the Gleeble system to design the press-hardening process to manufacture an automotive component, the B-pillar. Therefore, first of all, I'll explain what is this process in order to introduce you to some issue related to press-hardening process. Moreover, I'll give you some notion about tailored properties, since the B-pillar that we want to design must present tailored properties, which means to have some ductile regions with binitic microstructure and other high-resistant regions with martensitic microstructure. I'll show you how Gleeble system can help us during the design of tailored press-hardening process to obtain this B-pillar. Therefore, following, there will be detail about the method adopted to perform this study, and later I'll show you results and we will draw conclusion and further investigation. A scheme of press-hardening process is shown in this image. In particular, a blank, typically in high-strength boron steel, is heating for approximately 5 minutes at a temperature greater than 900 degrees to obtain an austenitic microstructure. After this blank is then transferred to a cooled stamping die, and after forming phase, the part is quenched within the die. The cooling rate must be greater than 27 Kelvin per second in order to obtain a martensitic microstructure that, that give to the component the high mechanical resistance. In fact, generally, this process is adopted to manufacture automotive structural component. In addition to the high strength of the component, at the end of the process, the other advantages of this technology are the reduction of spring-back phenomenon and the possibility to manufacture complex geometry. I already said that the high-strength boron steel is the material typically adopted in this process. In this figure, you can see that this steel have high ultimate tensile strength of about 1500 megapascal. However, recently Usibor 2000, so-called 37 manganese boron 5, has been added to the family of ultra-high-strength steel. This new material allows to reach higher performance with respect to its predecessor Usibor 1500, so-called 22 manganese boron 5. In fact, with the Usibor 2000, it is possible to reach a higher ultimate tensile strength equal to 2000 megapascal. Since this new Usibor is a new material, the mechanical properties of this material has not yet been implemented, for example, in autoform software. That is a thermomechanical metallurgical software that is able to numerically simulate press-hardening process. Therefore, it is able to design a process by evaluating the influence of process and noise parameters, and finally, it is able to estimate mechanical and microstructural properties of the component at the end of stamping process. In addition to the good intrusion resistance of hot-formed part, some components require, meanwhile, regions with lower strength to improve ductility for energy absorption. An example can be offered by B-pillar. As you can see in this image, B-pillar is a vertical support of a car that connects vehicle's roof to its body. The illustrated B-pillar is that of a commercial vehicle for which to obtain tailored properties, the current strategy adopted is to use a welded patch in the area that you want high strength. Moreover, to obtain ductile region in the bottom part of this component, a steel 340F is adopted. However, the aim is produce tailored component starting from a single blank without additional process step, adopting a tailored tool tempering approach, which consists of controlling rate during quenching phase. In particular, specific region of the tool, die and punch, are heated. Other are cooled in order to obtain, respectively, kinetic and martensitic regions. The hot tools are heated by means of heating cartridges. Instead, for the cold tool, cooling channel in which water flows are used. The goal is obtain this automotive B-pillar with binitic microstructure in these two zones and martensitic microstructure in the middle one. In fact, we have higher cooling rate in the martensitic region. On the contrary, binitic microstructure is formed with lower cooling rate. Now I show you why Gleeble Physical Simulator has been an efficient tool to support the design of tailored press-hardening process. First of all, as I have already said, the steel adopted to manufacture the B-pillar is the new Usibor, Usibor 2000. That is a new material recently developed by ArcelorMittal. Autoform simulation software in the R8 version, that is the commercially available version, has not yet implemented a car material with its flow behavior. Therefore, to keep this, hot tensile test with the Gleeble physical simulator was carried out. The flow curves were obtained in the austenitic field at the temperature and strain rates of interest for hot stamping process. However, to carry out this test on the Gleeble system, a careful design of specimen was performed. In fact, to remain in the austenitic field, it is necessary to respect cooling rates of about 27 Kelvin per second. To respect this cooling rate without using an external cooling system, we reduce the central section of the specimen to dissipate heat more quickly. This study was carried out with COMSOL multiphasic finite element software. Then, after designing the specimen, hot tensile tests were performed with Gleeble system, and the obtained flow curve were implemented in the Autoform software. This software allows to evaluate the influence of the process parameter on the stamped part. For the Usibor 2000, however, the austenite decomposition model has not yet been implemented in the commercial version of Autoform, so it is not possible to evaluate the final microstructure of the component correctly. To overcome this problem, we have varied the process parameters, in particular quenching time and tools temperature, to obtain the thermomechanical cycle in the soft zone, and we have physically simulated them with the Gleeble system. In this way, by subsequently carrying out tensile tests and hardness tests, it was possible to evaluate the mechanical properties and estimate the microstructure for each process parameter. In this way, it is possible to understand which process parameter must be used to obtain certain mechanical properties. Obviously, Gleeble allows you to do this much faster than post-forming tests. These activities are funded by MURE thanks to Pico and Pro project. Therefore, at the end of this year, we can compare experimental result with the result that will be obtained with the post-forming test in the industrial company. First of all, I'll show you the design of the specimen to respect a cooling rate of 27 Kelvin per second. In this way, we can carry out a hot tensile test in austenitic field. The final optimized geometry, as we will see, was also useful for the physical simulation of thermomechanical cycle of press-hardening process. In general, we investigated a new methodology to reproduce rapid thermal cycle on flat specimen. In this webinar, I'll show you only the application for hot tensile test. In this case, it is important to respect both high cooling rate and low thermal gradient. It is important to respect high cooling rate because we want to obtain the flow curve of the material in the austenitic field, since forming phase takes place in the austenitic field. Otherwise, if we don't respect high cooling rate, we risk to obtain at the end of the process ferrite, perlite or bainite. In the same way, it is important also guarantee a uniform temperature. This means have a minimum thermal gradient in order to obtain the flow curve exactly at the temperature imposed. We optimized the central section of the specimen as a function of length and width parameters. This study is carried out by means of a finite element model developed with COMSOL multiphysics software. In this model, heating phase, keeping phase, and cooling phase during Gleeble tests have been simulated. We found that if L and WE rising, cooling rate and thermal gradient reduce. Therefore, a compromise can be found in order to obtain high cooling rate and low thermal gradient. Finally, we have chosen a width of 10 mm and a length of 20 mm. With the chosen geometry, hot tensile tests with Gleeble system were carried out. In this slide, I show you the optimized geometry. On the specimens subjected to hot tensile test, four thermocouples were welded. The control thermocouple was welded in the center, while the others were welded at a distance from the center of -5 mm, 5 mm, and 50 mm. The experimental setup is shown down. These hot tensile tests were assisted by the extensometer that is characterized by aluminium rods in contact with the specimen. The gauge length is 10 mm, and in this length a uniform thermal gradient is present. The temperature range investigated is from 650 degree to 850 degree, and the strain rate range investigated is from 0.01 to 1 per second. Because I don't have much time, I'll neglect the results of mechanical characterization. I put as an example the flow curve in the case with hot deformation temperature of 750 degree and for all the strain rate investigated. In this other image, I superimposed thermal cycle on continuous cooling transformation diagram of USIBOR to 2000. For all investigated conditions, we are able, with the optimized geometry, to characterize the material in the austenitic field without adopted forced air. I'll neglect all details about mechanical characterization also because in other previous work, Gleeble system has been used to obtain the flow behavior of new material. I prefer, in fact, today highlight the support offered by the Gleeble physical simulator in the design of tailored press-hardening process. First, the obtained flow curve was used to create a card material of Usibor 2000 that we implemented in the Autoform software. Then, in this software, we varied quenching time and tools temperature to obtain a numerical thermomechanical cycle in one node of the soft region. Subsequently, these thermomechanical cycles were physically simulated in the Gleeble system. In this slide, I summarize the finite element model developed with Autoform software to simulate the manufacturing press-hardening process. On the left, we can see tools modeled in the Autoform environment. The tools are divided into cold zone and hot zone. For the cold zone, we imposed a constant temperature of 80 degrees. Meanwhile, for hot zone, we analyzed the influence of tool temperature. Therefore, we changed it from 430 degree to 500 degree. Also, the quenching time was varied from 5 seconds to 250 seconds. The aim is to obtain these two zones of the component soft, and the central zone must present high strength mechanical properties. For each quenching time and tool temperature, we extrapolated in this area thermal cycle and mechanical cycle. The optimized specimen geometry is used also for this test. In fact, this geometry has allowed to simulate correctly also the drawing and quenching phase, since a cooling rate of 100 Kelvin per second is reached in this phase. The only forced air without shaped specimen geometry would not have allowed to simulate physically this part of thermal cycle. The treatment specimen with the physical simulation are then subjected to microhardness test and to tensile test, with the aim to understand how quenching time and tool temperature affect mechanical properties of the component at the end of hot stamping process. Therefore, now I show you the results of tensile and microhardness test. As I have already said, the geometry of the specimen and also the experimental setup adopted to physically simulate the numerical thermomechanical cycle obtained by the Autoform software are the same as those used for hot tensile tests. On the right, you can see the graph of hardness values as a function of quenching time for all tool temperature investigated. We can observe that if quenching time and tool temperature increase, the hardness value reduce. You know that hardness is an indicative parameter of the microstructure. Therefore, it can be assumed that as the hardness value decreases, the percentage of transformed martensite decreases and the bainite percentage increases. This means that when the hardness value remains constant, it can be supposed that there has been a complete bainitic transformation. In order to verify the deformability in the ductile region of the component, tensile test by means of the Instron Universal Test Machine are performed. These tests have been assisted by the digital image correlation system provided by GOM. The digital image correlation system has allowed to evaluate the fracture deformability locally. The experimental setup is reported in the bottom figure. Uniaxial tensile tests are carried out on the notched specimen shown in this figure. These specimens were obtained machining the specimen subjected to physical simulation test. Notched specimens are adopted in order to force plastic deformation exactly in the central point of the specimen, which is the point where thermomechanical cycle is imposed, because it is the point where the control thermocouple is welded during the Gleeble test. Before the tensile test, the specimen, as you can see in this image, are sprayed with a white matte layer to avoid reflection, and then with a random distribution of small black points. On the right, I present some results obtained for the temperatures of 500 degree and 450 degree in the case of the minimum hardness, in particular for quenching time of 250 seconds. it can be observed that if temperature increases, the fracture deformability increases, but the ultimate tensile strength decreases. So we can conclude and we can say that thanks to the hardness result, we observe that if quenching time and tool temperature increase, hardness reduce. Hardness is an indicative parameter of the microstructure. Therefore, it can be assumed that as the hardness value decreases, the percentage of transformed martensite decreases and the binite percentage increases. When the hardness value remains constant, it can be supposed that there has been a complete binitic transformation. By evaluating the fracture deformability only in the maximum softening condition, a greater value is observed for greater tool temperature. In this condition, a lower ultimate tensile strength is reached compared to the case with lower tool temperature. The combination between another conclusion can withdraw is this. In particular, the combination between numerical tools with physical simulation test has proved to be an excellent strategy for an efficient design of the real stamping process. In fact, with Gleeble experimental test, it was possible rapidly estimate mechanical properties of the component after press-hardening process. Then finally, the obtained results will be compared with post-forming results that will be carried out at the end of Pico and Pro project in the SUSTA enterprise. So, with this, I conclude my presentation. So, thanks all for your kind attention. And if you have any question, I'm pleased to answer you. Thanks.